If BM25 kind of works, but top results still feel off, you probably need K1B tuning. I'll show a small end-to-end NDCG-driven tuning loop and how to read the trade-offs. You notice that some queries return decent documents, but the best matches are buried. That usually means the retrieval formula needs rebalancing, not a bigger model. By the end, you will be able to run a tiny Python loop that searches over K1 and B, measures quality with NDCG at 3, and interpret which knob moves which behavior. This is practical, low cost, and often fixes a lot of perceived relevance problems. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. BM25 tuning sits in the retrieval layer of a search stack. BM25 is a classic bag-of-words scoring function that ranks documents by term frequency, document length, and inverse document frequency. People reach for BM25 because it is fast, interpretable, and memory efficient compared to vector embeddings. A common downside is that BM25 uses surface term matching and misses deep semantic intent. So it is not a replacement for dense embeddings when semantics matter. But for many keyword or FAQ-style systems, it is the right tool. IDF is inverse document frequency, which measures how discriminative a term is across the corpus. NDCG at 3 is a ranking metric that rewards placing highly relevant documents in the top 3 positions. It accounts for graded relevance and position. Intuitively, we want highly discriminative terms to push truly relevant documents to the top, where NDCG at 3 will reward them. Imagine a tiny corpus of 4 short documents and 1 query. You will see which terms are rare, how BM25 scores those documents with default settings, and then how small changes to K1 and B shift the top results. This is exactly what we will build. A minimal pipeline that goes from corpus to IDF, to BM25 ranking, to NDCG scoring, to a grid search that picks the best K1 and B for this corpus. Now we'll create the tiny corpus and the single query. This snippet creates a tiny retrieval corpus and a single query. It sets up a few toy documents that share some overlapping words and a single user query that targets one of the topics. The point is to keep the data small, so you can follow each score change by eye. In the code, the documents are short strings. The query is another short string. And the snippet may also compute simple token lists or lengths, so later steps can reference term frequency and document length. In a real dataset, you would replace these 4 strings with your real documents, and the single query with a small set of held-out queries. Next, we'll look at term rarity that the query depends on. This snippet computes query term IDF to preview discriminative terms. It walks through each term in the query and computes inverse document frequency across the tiny corpus to show which query words will carry more weight. The snippet typically computes IDF as a small formula that depends on document counts, then prints or returns the IDF values next to each query token. That preview helps you understand why a rare term pushes a document up, while common stop words do not help. When you move to larger corpora, the same IDF intuition holds, just with more documents and more stable IDF estimates. Now we'll run BM25 with the default knobs so we have a baseline. This snippet ranks documents by BM25 with default K1 and B. It applies the BM25 scoring formula across the tokenized documents and the query, using the standard default for K1 and B to produce a ranked list. The code highlights the per-term contributions to each document score and shows the final ordering and raw scores. This baseline is the control for our tuning. In production, you might use a library implementation and feed in actual token counts. Here, the values are toy numbers, so you can see how term frequency and document length interplay under the defaults. Next, we'll measure how good that ranking is with a proper metric. This snippet scores the ranking with NDCG3 using graded relevance. It assigns relevance labels to each document for the single query, computes discounted cumulative gain up to position 3, and normalizes by the ideal ordering to get NDCG at 3. The snippet demonstrates how swapping a single document into the top 3 can change the score a lot, and why NDCG at 3 focuses our tuning on the very top of the list. In a fuller test, you would use multiple queries and average NDCG scores. But this small example makes the mechanics clear and shows why small parameter changes can move real quality. Now we'll search over K1 and B to find the best pair for NDCG at 3. This snippet grid searches K1 and B to maximize NDCG at 3. It runs the BM25 scorer for a range of K1 values and B values, computes NDCG at 3 for each combination, and returns the pair with the highest score. The snippet also prints a small table or a few best candidates so you can inspect the trade-off. Higher K1 amplifies how term frequency changes document score, while higher B increases the importance of document length normalization. In practice, you will pick ranges that make sense for your corpus length variance and expected term frequency. Then run this loop over your held-out queries to choose the final knobs. Recap: BM25 tuning is adjusting K1 and B to control term frequency strength and length normalization. Use it when keyword matching performance is critical and you need interpretable, low-cost improvements. One caveat: BM25 tuning cannot create semantic matches. If you need that, combine it with a semantic model. For a clear next step, run the same grid search, but widen the K1 range and add more held-out queries so performance stabilizes. That will show whether the selected K1 and B generalize beyond the toy example. It's short, practical IR helps. Subscribe and watch the IR videos.